So this is where we ended up in the last lecture, how to construct the Lagrangian. And we arrived at the point that the Lagrangian is completely defined given the number of fields and the internal symmetries. And the Lagrangian is constructed into the pieces, 4 pieces. The first piece is the kinetic energy terms of scalar, fermion, and vector field. And if your symmetry is gauge symmetry, then you have to replace the ordinary derivative with the gauge covariant derivative in these 3 kinetic energy terms of 3 different fields. And then the next piece is the mass sums of the fermion. You can add them directly in the Lagrangian only if your symmetry is not a chiral symmetry. But if it is a chiral symmetry in which the right-handed and the left-handed field transform in a different way, then you can't add it directly. You have to introduce it through spontaneous symmetry breaking. And that can be done if we add Yukawa interaction term. So a Yukawa interaction term by definition is a cubic term in which we couple 2 fermionic field, left and right-handed, along with the scalar field. We have to include all possible Yukawa interaction term in the Lagrangian as allowed by the symmetry. And then if we are breaking the symmetry spontaneously, we have to break it to produce the masses of the fermion through Yukawa interaction term and to give him masses to the gauge bosons. And if you have to break it spontaneously, you will break it through this last piece, which is symmetry breaking potential. So this is how you will construct it. And today we will apply this recipe to construct the standard model Lagrangian. Of course, I said that you can apply this recipe to construct any quantum field theory for any given symmetry and the fields. Okay, so coming back to the first point, that Lagrangian is defined if we are given the number of fields and the internal symmetry. So what precisely we are given? We are given, first of all, symmetry group. So, the internal symmetry define a group, so this group must be given. And then we also need to know how many fields you have and how they transform under the given symmetry group. So if this information is given, then we can proceed and we can construct the Lagrangian. So let's, before we define these things for the standard model, let's see that how the transformations are usually given the fields and given the symmetry group. If your group is U1 group, obviously the transformation is this one, where this constant y that is called hypercharge, which we can choose its value arbitrarily. So what we typically do, that rather than defining this transformation completely, we just specify the value of this y charge, and then you can write your transformation yourself. So that's how you specify the transformation of a field if your group is U1 group. And if your group is SUN group, then in this case we specify the representation of the group, mean which representation is followed by the field to get transformed. For example, if you have 2 fields, then and the group is SU2, then these 2 fields may transform by 2-dimensional representation of SU2. So we just specify that the fields, the doublet, they transform by 2-dimensional representation. And of course, you can write the transformation explicitly in this form, where TA, these are the generators of SU2 in 2-dimensional representation, which are simply the polyspin matrices. And if you have, say, 3 fields, and the group is still SU2, then these 3 fields, they form a triplet, and they may transform by 3-dimensional representation of SU2. And in this case, the transformation is exactly the same, but the generators, they are not 2x2 matrices, they are 3x3 matrices. 3x3 matrices, but they furnish the representation of SU2 group. And you can also have, for example, by the way, 1-dimensional representation of SU2. in one-dimensional representation, you have single field, and in one-dimensional representation, these generators are always zero. So that means that the field remains invariant if it is transforming by one-dimensional representation of SU2. So given this basic knowledge, so let's define these two things, the first two things for the electroweak standard model. In case of electroweak standard model, the symmetry group is SU2 cross U1. This cross means that the group is defined to the direct product of two groups. And the direct product means that the group elements are defined to the product of the group element of the first group and the second group. So that simply means that if you just multiply or combine the transformation as defined by the first group and the transformation defined by the second group, you will get a transformation by the direct product of these two groups. So this is the basic symmetry on which the electroweak standard model is based. There is L over here in the subscript, and we will discuss it in a moment, that what this L means. And the Y over here, that corresponds to the Y charge. So the conserved quantity corresponds to this U1 symmetry that is supposed to be a Y charge. Just a name, not specific meaning to it. And then you write this expression over here. So that means that this symmetry will be broken spontaneously. But when you break the symmetry spontaneously, it is possible that the part of the symmetry remain intact. It is not broken spontaneously. So this part, that is U1 symmetry. So you break this symmetry, but you do not break it completely. A part of this symmetry remain intact. The reason that we do so is that if you break the symmetry completely, then all the gauge bosons, they will get the mass. But you know that out of the 4 gauge bosons, W plus minus Z and photon, we want photon to be massless. Or we want to have the masses only for W plus minus Z not boson. So that's why we have to break it partially, not completely. And once you have defined your symmetry group, then we come to the next point, that which fields you have and how they transform under the given symmetry group. Okay, so in electroweak standard model, we have the matter fields, in which we have the quark fields. We have 6 quark fields corresponding to 6 flavors of the quark, and 6 lepton flavor corresponding to, again, 6 flavors. And this table over here, the information which are provided in this box, that actually provide the answers of this question, that how these fields transform under given symmetry group. So let's see that how we interpret the information given in this box. Okay, so first of all, we talk about left-handed quarks. Left-handed quarks, that means that we are decomposing each fermion field into the left chiral field and the right chiral field. And the left-handed mean I'm talking about left chiral field. So left chiral field, for which I use this symbol QL, I, and I will explain in a moment that what this I means. So how this field, the left-handed quark field, how they transform under SU2 and how they transform under U1. That is defined through these two numbers written over here. This 2 corresponds to the SU2, and this 2 simply means that the left-handed quarks, they transform by 2-dimensional representation of SU2. And this second number, that is defining out that how these fields transform under U1Y. And this transformation is defined by specifying the value of the Y charge only, as I mentioned in the previous slide. So given this information, you can explicitly write the transformation, okay? How the left-handed quarks will transform under SU2 cross U1. But you don't have to write it, you just have to understand that they transform by 2-dimensional representation of SU2, and when they transform under U1, the value of the Y charge is taken plus 1/6. Okay, so but the question is that since I'm saying that these fields transform by 2-dimensional representation, and in 2-dimensional representation you have 2 fields which get transformed, so which 2 quarks, left-handed quarks, get transformed? The 2 left-handed quarks which transform, or which act as the basis for this 2-dimensional representation, are up-type and down-type quark. So this is one doublet. Of course, if you suppose that the quarks are left-handed. And then this is another doublet. And then this is another doublet. So we have three doublets corresponding to three generations. And this index about I, this index I, that is actually the generation index. For I1, when I is 1, I'm referring to these left-handed doublets. For I2, I'm referring to these left-handed doublets. And for I3, the doublets are formed by top and bottom fields. Okay, so this is the point where we define how the left-handed quark transform under SU2 cross U1. But what about the right-handed quark? We have decomposed the field into the left and the right-handed field. So how the right-handed transform? So the right-handed U quark means up-type quark, including up, jump, and top. So the right-handed U quark, they transform by this. So let's interpret the information which is provided in this bracket. The first number is 1. So that means that the right-handed U quark transformed by one-dimensional representation of SU2. And we previously looked that when you say that the field is transformed by one-dimensional representation, it is actually invariant. Because in one-dimensional representation, the generators are 0. And the value of the Y charge is plus 2 by 3. And then we talk about the right-handed D quarks. And D quarks mean the down-type quark, including down, strange, and bottom quark. They are also the singlet of SU2, and the value of the Y charge is minus 150. So for these fields, we use the symbol URI. DRIR stands for the right-handed, and I is again the generation index corresponding to three value of I. This field is referring to up, jump, and top quark. And then we come towards the leptons. The left-handed leptons, they are the doublet of SU2, just like the left-handed quarks. And the value of the Y charge is minus 1/2. Okay? So, since I'm saying that the doublet, so the question is that which left-handed lepton act as a doublet? The answer is this. Electron and electron neutrino. The left-handed electron and the left-handed electron neutrino, they act as a doublet. This is the first doublet, this is the second doublet, and this is the third doublet. So for this we use the symbol L, I. L stand for lepton, and this L is the subscript stand for the left-handed, and I is the generation index. And then what about the right-handed leptons? So here we again make a distinction between the right-handed charged leptons, which mean I'm talking about electron, muon, and tau, and right-handed neutral leptons, for which I use the symbol V leptons. I'm referring to the neutrino in this case. The right-handed E lepton, mean the charged lepton, they are the singlet, and the value of the Y charge is minus 1. And whereas the right-handed V leptons are concerned, we know that they do not exist, so we don't have to put in the Lagrangian. And since we are breaking the symmetry spontaneously, so we need the symmetry breaking potential, which is defined through a scalar field. So we need a scalar field as well. So to break the symmetry in this way, the scalar field which we require, that must be doublet of SU2. If you suppose it's a singlet, you will not be able to break the symmetry in this way. So the scalar field which we suppose, that is a doublet of SU2, and its Y charge is plus 1. And corresponding to the scalar field phi, we also define another scalar field, phi delta. That's not an independent field. That defines from the phi static. And since we will use in the construction of the Lagrangian, so we can see easily that if phi is a doublet, then the phi delta is also a doublet. But its value of Y charge will be minus 1/2, because phi delta is defined to the static, the complex conjugate of phi. So these are the ingredients. The information which are provided in the box, they just answer this question, that how field transform under the given symmetry group. Okay, so once you know the answers of these two questions, that what is a symmetry group, what are the fields, and how they transform, then you can go on to construct the Lagrangian by using the recipe which we have discussed. So and by the way, one more thing I forget to mention, that why these values of the y charges are support. Why the y charges in this case is taken +1/6, +2/3, -1/3. What's specific to these values? So you see that when you will be constructing the standard volume, then you will constrain on it. It will produce the electromagnetic interaction of these particles correctly. And in the electromagnetic interaction, the fields couple in this way. And the coupling constant is equal to Q into E. So Q is the charge and E is the coupling constant. And this charge, that turns out to be the sum of T3 plus Y. Y is the Y charge, and T3, that's a third component of weak isospin. SU2 has 3 generators corresponding to this. We have 3 conserved quantity, and the third component, the third one, that is represented by T3. So this electric charge that is related with the Y charge in this way. And this electric charge should come out correctly. For example, for up quark, the electric charge which should come out, that should be +2/3. For the down quark, it should be -1/3. And for the neutral electron, it should be 0. And for the charged electron, it should be -1. And that would happen only if you choose the value of the Y charges in this way. So if you just use this equation, put the value of electric charge and T3 is 0 if you are talking about singlet, and if it is doublet, then T3 is either +1/2 or -1/2 for up or down type quark, and then you can calculate the value of the Y charge from this equation, and it turns out that you get exactly the same value. So there's nothing mysterious about the choice of the value of the Y charge. Of course, you can talk about that why the value of the Y charge is taken +1/2 in case of Higgs field, because we don't have any prior knowledge of the charge of the Higgs field. But I can answer in the next slide that why this value is taken +1/2. And finally, that how we guarantee the invariance. You see that if you have any interaction term in which you have, say, 3 fields, and these 3 fields transform by U1, then in each transformation, an exponent will be contributing with the value of Y charge in the argument. And if we are transforming these 3 fields, then there will be 3 exponents, and the Y charge will be added. And this exponent will be 1 if the sum of the Y charges is 0. So the invariance is guaranteed for U1 symmetry if the total hypercharge or Y charge of all the fields in a term is 0. Okay, so you have to, whenever you will be combining the fields to construct an interaction term, you can combine only those fields in which the sum of the Y charge of these fields is 0, and that will guarantee the invariance. And in case of doublet, in case of SU2, the invariance is guaranteed if you combine a doublet with a doublet. If you combine doublet with a singlet, the result will be a doublet, which is not invariant. The singlet can only be constructed if you combine doublet with doublet. So when we are constructing the terms, then to guarantee the invariance in the SU2, you have to make it sure that 2 doublets are combined. Okay, if you just have single doublet, the term will not be invariant in the SU2. Okay, so let's now apply the recipe that first we have to construct the kinetic energy term of the scalar field, fermion field, and the vector field. And since our symmetry is a gauge symmetry, so we have to replace this ordinary derivative with the gauge covariant derivative. And if your field is a doublet, then the gauge covariant derivative will be containing 2 parts. This part is coming from SU2, and this part is coming from U1 symmetry group. But if your field is a singlet, then in this case the generators are, SU2 generators are equal to 0. So that's why in this case the gauge covariant derivative will be simply equal to this one. Okay? So what will be the value of the gauge covariant derivative in different terms? That depends that whether the matter fields in these terms are singlet or doublet. Okay, so let's first talk about the kinetic energy term of the fermion fields. So all these fields are the fermion field. So this is the gauge invariant kinetic energy term of the left-handed quarks, then U quarks, then B quarks, then left-handed leptons, and this is the kinetic energy term of the right-handed charged leptons. And since we do not have the right-handed B leptons, so we don't have to put the kinetic energy terms. So we have 1, 2, 3, 4, 5 kinetic energy terms. And in all these kinetic energy terms, you see that in this term, the field is doublet, and then it is doublet over here. So in these two terms, gauge covariant derivative will be equal to this one. So what will be the value of the y charge? That will be different for Q field and different for L field. And in these three terms, this one, and this one, the fields are similar, so therefore the gauge covariant derivative will be equal to this one. So although I'm using the same symbol, D in all these terms, but this D is not exactly same in all these three terms. And since we have two groups, SU2 and U1, so corresponding to SU2, we have 3 generators and 3 gauge field, and corresponding to U1, we have 1 gauge field, and these are the kinetic energy terms. These are the kinetic energy term corresponding to the gauge field of SU2, and this is the kinetic energy term corresponding to the gauge field of U1. Okay, since our symmetry is a chiral symmetry, and you can see the chiral symmetry because we are supposing that the left-handed and the right-handed field transform in a different way. So therefore, the mass term of the fermion fields that cannot be added directly to the Lagrangian, that would break the symmetry. So we have to add it to Yukawa interaction term. So what will be the Yukawa interaction term? As I said earlier, that in the Yukawa interaction term, you combine right-handed fermion field with the left-handed fermion field along with the scalar field. So what we have to do now, that we have to construct all possible Yukawa interaction terms which are dictated by the symmetry, which are invariant under this set of transformations. And it turns out that in this case, we can have 3 Yukawa interaction terms. The one in which this D is coupled with Q, and then U is coupled with Q, and E is coupled with L, and they have Hermitian conjugate as well. You can see that in each of these terms, the sum of the y charge is 0. If you add the y charge of the phi field, D field, and Q field, the sum is 0. So that is actually because the term should be invariant in every term. And in each term, you are combining doublet with the doublet. This is doublet, this is also doublet. So that also gives us SU2 invariance as well. So these are the only 3 possible Yukawa interaction terms. And the most important thing is this one. You see, it need not to be important that the generation of the Q field and the generation of the D field, that need not be exactly same. So that's why we use different indices, different generation indices for them. We will still have the invariance. And since the fields depend on the generation, so the coupling constant, that would also depend on the generation. And then finally, since you have to break the symmetry spontaneously, you need a symmetry breaking part as well, which is this one. Okay, so you have a Lagrangian, standard model Lagrangian, okay, but that's not complete. There are certain steps which we have to apply. The most important step is that we have to apply this symmetry breaking. So that means that we have to make a choice of a ground state configuration of the scalar field, and then we have to redefine it and apply this redefinition to the Lagrangian. So this is one simplification which we have to do. The second simplification which we have to do is that we will see in a moment that the mass matrices of the different fields, mass matrices mean the matrix which defines the masses of these fields, that's not diagonalized. Okay, so that means that the masses of these fields are not defined. So we'll prefer to use the fields in which the mass matrix is diagonalized. So we will apply different sort of transformations so that the mass matrices are diagonalized. These are the only 2 steps which we have to apply. Break the symmetry spontaneously if you have to, and obviously in this case we have to break it, and diagonalize the mass matrices of the different fields in the Lagrangian. So that is the rest of the step which we have to do. Okay, so let's start with the Higgs sector. In the Higgs sector, we just focus on a certain terms in the Lagrangian, the terms in which contain the Higgs other than Yukawa interaction terms. So that includes the kinetic energy term of the scalar field and the symmetry breaking potential, right? So in this case, the ground state configuration, the gauge is the gauge covariant derivative is this one in this case, because you see scalar field is a doublet, So we should have this term over here as well, and that is the y charge of the stable field. The ground state configuration in this case, that's satisfied, that's equal to this one. So from this you can find an infinite set of degenerate ground state. We choose one of them. Okay? So in this case the ground state configuration itself doublet because your field is a doublet. And then you redefine your field in terms of a new set of field whose ground state configuration is 0, and that's the redefinition. And you can see that the new fields, which are eta and 3 chi field. The chi field come with the index A, which has 3 possible values corresponding to 3 generators of SU2. So if you put chi and eta 0, you will get this ground state configuration. So that's the correct redefinition. But once again, we would like to work with the unitary gauge, where this chi field that can be removed by applying the gauge transformation. So after the gauge transformation and removing this chi field, the redefinition is simplified into this one. And then you just have to put back in this Lagrangian and simplify it. So I'm leaving this as an exercise for you. After putting it back in this one, the simplified form into this one. We just look at the important step which we have to carry out after this simplification. So first is the kinetic energy term of the eta field, second is the mass term, and then it's the cubic interaction term, quartic interaction term, and then the rest of the terms which are highlighted yellow. These are the interaction terms in which the eta field interact with the gauge field, right? And these interaction terms actually also contain the mass term as well. For example, if you just look at the first term, you have nu plus eta squared. Nu is a constant, the constant of the vacuum expectation value, and then eta is a field. It's a function of space-time quantity. And you have the sum of these two entities in a square. Now obviously, one of the terms will be equal to nu squared, which is just a constant, and when this nu squared will be multiplied with this factor, it will be a quadratic mass term. So mass term is coming from this part as well as from this part, and this part as well. So let's separate the mass terms. And I would like to separate the mass term of W3 and B fields only. Okay, so these are you see that we have 4 gauge fields, W1, W2, W3. These are the gauge field corresponding to SU2, and B field, the gauge field corresponding to U1. So we just separate W3 and B field. So these are the mass terms of the W3 and B field. So if I write these mass terms in the matrix notation, then inside these 2 doublets, we have a matrix, 2 by 2 matrix, and you can see this matrix is not diagonal. So that means the masses of these fields are not defined. Okay, so that's the point which I was making, that we have to apply different sort of transformation to diagonalize the mass matrix, because we would like to work with the field whose masses are defined. So incidentally, we see that this mass matrix is a symmetric matrix, and it's also contain real numbers. These are just the 2 topic constants. And this real symmetric mass matrix can be diagonalized by an orthogonal transformation. And in 2 dimension, the orthogonal transformation is this one. So to diagonalize it, we transform W3 and B field into another set of field. We call them Z and A field. And if you apply this transformation over here, then W3 and B, they turns into Z and A, and the mass matrix now becomes the product of 3 matrices. The original mass matrix and the 2 matrices which are coming from the orthogonal transformation. So if you combine these 3 mass matrices, the total mass matrix will be this one. And we want to have it diagonalized. Okay? And that will be diagonalized if the off-diagonal terms are 0. And you see that off-diagonal term, first of all, they are at a leader. And each off-diagonal term is a product of 2 factors. So I can make it 0 by assuming that any one of the factors is 0. So either I would say that this factor is 0, or I say this factor is 0. Okay? Either way I can make it diagonal matrix. Now if I say that this factor is 0, then obviously the off-diagonal term becomes 0. But what happened to the diagonal terms? The first diagonal term is actually the square of this factor which I am taking 0. The first diagonal element also becomes 0. But obviously the second will not be 0. So what happens? So if the first diagonal element is 0, then the mass of the Z field will be 0 and the mass of A field will be non-zero. But Z field we want to correspond to Z bosons, so we don't want to make massless. It's an A field, which is electromagnetic field. We want to make it massless. So for this, all you have to do is to assume that it's a second factor which is 0. Because when you take the second factor 0, then the second diagonal element becomes 0 and the mass of the electromagnetic field is 0. So this is precisely what we do. So to diagonalize this mass matrix, we fix the value of theta. The theta which was introduced to the linear transformation, we fix it in such a way that this is equal to 0. That means that the theta is related to the coupling constant. And if we do it, then this will be the mass matrix and the masses of the Z will be defined as well as A is also defined. One is non-zero, the other is 0. So this is how you diagonalize the masses. So you see that after this diagonalization process, the mass of W plus minus field is defined through this field. In this case, no diagonalization is required because it is already diagonalized. The mass of Z field is defined through this term, and there is no mass term of the A field, and the rest are the interaction term between the W and Z field with the eta field, which will be acting as a Higgs field. The most interestingly, we notice that since these masses are introduced through spontaneous symmetry breaking, and whenever you introduce these symmetry breaking terms through spontaneous symmetry breaking, the parameters are related. So that's why we notice that the mass of the W boson is not an independent parameter. It is fixed by the value of the coupling constant and the vacuum expectation value. And same applies to the mass of the Z boson. It's not an independent parameter. Okay? So by just verifying these relations, then we can verify that the masses are being generated by breaking the symmetry spontaneously rather than breaking it explicitly. And then these are the interaction terms. This interaction term, that's the interaction term of the W field with eta field, Higgs field, and this is the same term also is the interaction of the W field with 2 Higgs field, this one, and then you have the interaction of the Higgs Z field with 1 Higgs field and 2 Higgs field. So this is how you diagrammatically represent the interaction terms. Okay, so once we are done with the Higgs factor, and from the Higgs factor we learn that the masses of W3 and B fields are not defined. The masses of Z and A fields are defined, which are related with W3 and B field to a linear transformation. But if you come back to the kinetic energy term of the fermion field, in this we have the gauge covariant derivative, and these gauge covariant derivatives contain B field and W1, W2 and W3 field. So we also have to transform them into Z and A fields. Okay? And when we do it, so we get this part. This is the part coming from these 2 terms. We call it the leptonic part. And then we have the hadronic part coming from the first 3 terms. So here we have all sort of interaction between matter fields and the gauge field. Okay, so we have actually 4 interaction terms in this part. This is the interaction term in which the charged lepton is going into the neutral leptons. So we call it a charge changing current. This is also the similar kind of interaction in which the charge of the field is changing. But in the rest of the interaction, the charge of the field is not changing. Neutrino remains neutrino, electron remains electron. And then this last interaction, that's electromagnetic interaction. And where we notice that the electromagnetic interaction is vector in nature, the current is vector, and you see that you are getting it, its coupling constant is also correct. Okay, it's a minus E, that's the coupling constant you should get for electrons. And in the case of quarks, we again have the same type of interaction, charge changing interaction with this CC current, charge changing current. D type quark is converted into U type quark, U is converted into D, U remain, U, D remain D, to the coupling with the Z bosons, and then we have electromagnetic interaction. That's the electromagnetic interaction of U quark, and that's the electromagnetic interaction of D quarks. And notice the coupling constant over here is plus 2 by 3 E. It's because of particular choice of the white charge which we assumed in the beginning, and it is also minus 1 by 3 E. The interactions, electromagnetic interactions, they are vector in nature. So the current is vector. And these CC interactions, they are B minus A interaction is a vector, and the second is axial vector, so that's why we call it B minus A interaction. And the yellow one, they are the mixed interaction, in which they appear a constant A, B, C, D, which are defined as follows. So this is what, these are the interactions which we get after we transform the W3 and B field into the Z and A field as dictated from the sector. Okay, now coming back to the Yugawa interaction. So how they generate the masses of the electrons. So these are the three Yugawa interaction terms which we identify at the beginning. They exist only three invariant terms in this case. So each term contains the scalar field phi. The second term contains the scalar field phi tilde, but the rest of them they contain the scalar field phi. And psi is equal to this one. So, and whereas phi tilde that's equal to this one, we have to apply this redefinition in these terms, and we also have to understand that Q is a doublet, D is a singlet, U is also singlet, and this L that's not unfortunately written over here, that is also doublet. So if you apply this redefinition over here, then obviously what you will get? You will get a term like this one. Okay, so you have the right-handed down quark coupled with the left-handed down quark, and the next factor is mu plus eta. And then you have the right-handed up quark coupled with the left-handed up quark, and the rest of the factor is mu plus eta, right? I'm just talking about the first two terms, not the third one. And you see, eta is field, so when eta will be multiplied with these terms, it will give rise to a cubic interaction term. But nu is just a constant. And when this constant will multiply with this term, it will give rise to the mass of speed. Okay, so this is the mass. You can see that these terms will produce both the mass terms as well as the interaction term. And here we notice that this mass matrix, that is an arbitrary matrix. So symmetry doesn't tell us that, doesn't imply that this mass matrix must be diagonal. So even if I suppose the non-diagonal, the term is allowed by the symmetry. So that's why we will suppose that it is non-diagonal, and if it is non-diagonal, then we have to diagonalize it through another set of transformation. So first of all, for this process, we first of all suppress the index I. This is a generation index, and it will have three possible values, and we write the same term. But once you have suppressed this index, then this is column matrix, this is 3 by 3 matrix, and this is a row matrix containing 3 elements. Okay, the same applies to this part as well. So this is how you understand these terms. And this 3 by 3 matrix, which is called the mass matrix, we want to diagonalize it. And we can diagonalize it by doing this generalized similarity transformation. So A, B, and B, D, similarly AU and BU, these are the transformation matrix through which we transform these mass matrix into the diagonal matrices. So once it is done, we have to simply put the value of M and M tilde from these general rules into these two terms, then we get this answer. So here you see that if you compare this term with this one, here you have the mass matrix M, which is non-diagonal, and here you have the diagonal mass matrix. But when you have a diagonal mass matrix, then this field dr, that is get transformed by this transformation matrix. And similarly this dl field, that is transformed by this transformation matrix. So we redefine the fields, we represent them by d prime, which is related with d to this transformation matrix. Then we define DL, which is related, DL prime, which is related to DL to this transformation matrix. And similarly, you define UR prime and UR prime as well. And if you apply these definition over here, you get these terms. So if you contrast this term, for example, with this one, this is exactly the same term, except that the mass matrix has become a diagonal matrix, and the fields have been transformed. They have been transformed by linear transformation. So unprimed field, the masses of unprimed fields are not defined because the corresponding mass matrix is not diagonal. But the masses of the prime field, they are defined because the corresponding mass matrix is diagonal. So from the same term, we get, as I said earlier, we get the mass term when the nu is multiplied, and when the eta is multiplied, we get the interaction term. So this is the interaction term of the Higgs field with the quarks, downside quarks, upside quarks, and similarly you can just look at this term, you can generate this interaction. And most importantly, we see that the coupling constant of interaction term is directly proportional to the mass of the particle. So greater the mass, the greater will be the interaction. Okay, so we have to go back to the kinetic energy term. I mean, you see the kinetic energy term, in the kinetic energy term, we still have unprimed quark fields. We have to convert them into the primed quark fields because the masses of the unprimed quark fields are not defined. Okay? So that's why the transformation matrix, transformations which were dictated by looking at the Yukawa interaction term, we have to apply these transformations in the kinetic energy term as well. We already have constructed this, but now we have to transform unprimed fields into the primed fields. And unprimed fields and the primed fields, they are related to these four transformations. And each transformation is defined through a 3x3 matrix. So what would happen if I apply these transformations over here? Before we look at the result, but let's look at some general result. So suppose you have an interaction term containing this type of current. It's a mixed current. And this is decomposed into the right-handed and the left-handed field. And since it's a mixed current, so that's why the coupling constants, they are not exactly same, KR and KI. Okay, so what happened in this case? The right coupled with the right and left coupled with the left. But since the transformation of the right-handed matter fields, whether they are E quarks or they are U quarks, that's same. So when this will be transformed, when we this convert this unprimed field into the primed field, and similarly if you do it over here, then the transformation of U and UR bar, that will get cancelled. Okay? So that's why that even after converting the field into the primed field, you will get exactly the same term. So the transformation matrix will cancel if you have this type of current. But on the other hand, if you have this is a neutral current. We have charge current, and we have the charge current in the first two terms, which are highlighted blue. And these are the neutral currents. So on the other hand, if you have a charge changing current, in which, for example, D goes to U or U goes to D, and if I will decompose it, and in this case, this is V minus A interaction, so when we decompose it in the left and the right-handed fields, we generate only the left-handed fields. So again, left coupled with the left. But it's a down left which is coupled with the up left. And the transformation of down left and the up left, that is not defined to the same transformation matrix. In this case, the transformation matrix is AD, and in this case, the transformation matrix is AU. So that's why when we transform these unprimed field into the primed field, the transformation matrix is not completely cancelled. So this AU is not cancelled with this AU inverse. Each one of them is a 3x3 matrix, so we are left with a 3x3 matrix defined to the product of these two matrices. So what we expect that what would happen that when we apply these transformations into these interaction terms, so there are two types of interaction, and actually three types of interaction. interaction in which the charge of the field is not changing. Okay, so these are highlighted yellow and red, and the interaction in which the charge of the field is stable. So in these interactions, there will be no impact of these transformations. But in these two interactions in which the charge is changed, there will be a leftover matrix. This leftover matrix is called the CKM matrix, and this CKM matrix is actually implying that any down-type quark can convert into any up-type quark. So appearance of the CKM matrix in CC current, charge changing current, interaction implies that any down-type quark can go into any up-type quark to this. So these are the corresponding interaction terms of charge changing interaction. This is the interaction with Z boson, and this is the interaction with photon. So in this case, the flavor is conserved, whereas in this case, the flavor can change. Okay, so that is represented by saying that we can have different value of alpha and alpha over here. Okay, so then finally we talk about the kinetic energy term of the gauge field. They are still written in terms of W free field and B field. We have to transform into Z and A field. That's to these linear transformation. That's the previous calculation. But once you do it, you get these interaction terms. So from this sector, we get the cubic interaction of electromagnetic field W plus minus field, quartic interaction of W fields, and then quartic interaction of W and photon field, cubic interaction of Z with W field, and the quartic interaction of that W with the Z field. So these are the interaction terms that are generated from the gauge sector. Okay, so finally we include all these interaction terms which are being generated. So first of all, we have FFV interaction. FFV means two fermions are coupled with a vector field. So these are the interaction which I just showed in the previous slide. And then we have FFS interaction, two fermion field coupled with a scalar field, which is fixed field in this case. We have VVS coupling, we have VVSS coupling, two vector fields coupled with two scalar fields. And we have triple scalar field and the quartic scalar field interaction. And then we have a triple vector field and the quartic vector field interaction, just shown in the previous slide. So these are the possible interactions which exist in the standard model. Okay? So each interaction comes with a coupling constant which is written over here. And if you just look at the parameters which appear in the standard model, you can count them. First of all, we have, I'm just talking about first the list of independent parameters which we have in the standard model. We have E, that's the electric charge. And then we have the theta that came when we mixed W3 and B fields to diagonalize their mass matrices. Then we have VEF, vacuum expectation values. We have the parameter lambda. We have the masses of the leptons. There are 3 leptons, and there are 6 leptons, but in this minimal version of the standard model, neutrinos are massless. So we have 3 masses of leptons, 6 masses of quarks, and this CKM matrix, that is actually a unitary matrix, and that's why it is parameterized by 4 elements, 4 independent parameters. So on the whole, you have 1 plus 2, 3, 4, 7, 13, and then plus 4, 17 parameters. So we have 17 free parameters in the electroweak sector of the standard model. And then we have certain dependent parameters. For example, the mass of the W boson. That's not a free parameter. It's just fixed from the value of these parameters. The mass of Z boson, the mass of the Higgs, that are also fixed from these parameters. And the coupling constant G, that is also fixed by these parameters. Okay, so finally, just 1 or 2 minutes. So is it all what the standard model offers to us? The answer is no. So you see that if you look at the interaction terms, which are depicted by these pictures over here, they are all the interaction term in which the total dimension of field is 3 or 4. Okay, so that means actually we have constructed the standard model only by relevant and marginal couplings. If I treat the standard model as an effective field theory, it's applicable up to a certain finite scale of energy, then we can also include irrelevant couplings in the Lagrangian of the standard model, meaning the couplings whose dimension is greater than 4. Okay? So what happened that when we try to complete the standard model by these irrelevant couplings? Of course, and we have discussed it earlier, that when you are applying the standard model at low energy, the effect of irrelevant coupling can be ignored, and it's a good approximation to use only the cubic and the quartic interaction term. Okay, but the standard model is incomplete without the irrelevant coupling, which become important at high energy. So far we have, this is the complete standard model Lagrangian. So far we have just developed this part of the standard model Lagrangian from the couplings with dimension 4 or less than 5. Okay, so you can go on to find 5-dimensional interaction, 6-dimensional interaction, and so on, right? Now these interactions will be suppressed by a scale factor. It's a simple dimensional analysis tells us that since the dimension of Lagrangian is 4, okay, so this is 4 over here and this is also 4. So to make its dimension 4, we have to suppress it by the scale factor. And its dimension is 6, so we have to suppress it by square of the scale factor. So first of all, we need to understand that what's the meaning of this scale factor. In effective field theory, the higher order interaction terms are always suppressed with the scale factor. And this scale factor defines the scale where the theory breaks down. I said we are treating it as an effective field theory. It is applicable up to a certain finite scale of energy. What is that scale up to which it is applicable? That is defined by this factor. Okay, so we expect that this may be the gut scale, lambda naught, it may be the Planck scale, we don't know. But I will see that we can argue, we can actually try to fix the value of this scale factor from this kind of data. Okay, so what about these higher order interaction terms? These higher order interaction terms must be Lorentz invariant, they must be gauge invariant, and they must have the same symmetry which exists in this part, and they must contain exactly the same fields. Okay, so when you are constructing these high dimensional interaction terms, you have to use same fields, I mean no new particle or no new field, right? And when we do it, we find at 5 dimensions, there is only one coupling which we can construct, which is Lorentz invariant, gauge invariant, and constructed from the same field. And this coupling is this one. It contains a scalar field and the lepton field, and when you put the value of the scalar field in terms of the Higgs field, it turns out that this is basically the mass term of neutrino. Okay? So that means that the mass of term of the neutrino can be generated from the 5-dimensional interaction term. And most importantly, we see that the mass of neutrino that is inversely related with the scale factor which I mentioned earlier, the scale up to which this theory is applicable. So if we use a limit of the mass of the neutrino, we can fix the limit of the scale factor. So if I suppose that the mass of neutrino is less than 0.1 electron volt, then lambda naught, that should be greater than 10 to the power 15 Jeff. Almost same as the Bird scale factor. So it's interesting that the standard model is itself telling me that up to which scale it is applicable. Okay, and remarkably, it tells me that up to the scale, Bird scale, it will be applicable. And something same is obtained when you go to 6-dimensional interaction terms. In this case, we have 90 interaction terms. And some of these interaction terms violate the baryon number. And because of this baryon number violation, proton can decay, right? And if we calculate the decay constant of the proton, from the terms which violate the baryon number, we find that this decay constant is inversely related to the fourth power of the scale factor. So if you have, if you know the limit of the lifetime of the proton, current experimental limit, which is, I think, greater than 10 to the 34 years, we can fix the limit on this scale factor. And interestingly, we find more or less same answer as we get from the value of the scale factor from the mass of neutrino. So that's the final slide. So you see that right now we are standing over here. Okay, we have gone to the scale of 10 to the minus 17, and at this scale, to go up to this scale, we require energy of 10 TeV. And at this scale, we find that leptons, quarks, gauge bosons, and Higgs boson, they are the fundamental particles. And we are looking ahead. Okay? And there is a possibility, there is nothing ahead. There is a desert over here, and everything we will discover here, we will be able to explain it through this higher order interaction term. And the standard model will really break down at the scale, grand unification scale, which corresponds to this energy, and we don't know when we'll be able to explore it. It's just a possibility, right? I mean, the standard model, we know the standard model is incomplete. For example, it doesn't explain the existence of dark matter. So we need another theory. We have to replace the standard model, even in this region, with a new theory which will explain the dark matter. Okay? But if the dark matter is explained by some other ways, like modified gravities, then there is a possibility, it's just a possibility, I'm not endorsing, I'm not saying that this is the case. There is a possibility that there will be no new theory, okay, unless we go to this scale. Thank you very much. So, questions?
Thank you. Could you go back to the slide for the Lagrangian for the Higgs sector? Yeah, the next one. Yeah, so in the kinetic term for the complex scalar field, I see that you are contracting a covariant derivative with a normal derivative. Like, is that not?
It's a typo.
Yeah, it's
a typo.
Because it's not a Lorentz invariant.
The gauge covariant derivative. Yes.
Okay. So, the other question when you were talking about interactions, all different kind of interactions that occur in the standard model, you showed that there is another interaction that vector field couples to itself like four times.
Yeah.
We know there is only one vector field in the standard model at right now, right? That's the electromagnetic field. So
we have W field, Z field, there are also the vector field. Yes. You want to see that also. Yes.
So the vector field that couple, like the quartic term that you were talking about, like,
yes.
What are those vectors? Are they only the electromagnetic field, or they are electromagnetic field coupling with others?
They are not electromagnetic field.
Oh.
Z field is a vector field. W field is a vector field.
Okay.
All these are the vector fields.
Okay.
So you can't say we just have electromagnetic field as a vector field.
Any other comment? Questions? If not, let's thank you. Thank you very much for being with us and being a part of this group. We are really grateful to you. You're always been our savior. Thank you very much. Thank you. Thank you.